microstructure formation, kinetics in substantial alloys, kinetics of melting and solidification in glass forming alloys, different types of effects, non-equilibrium effects, and high driving forces for phase transformations, microstructure formation, and one of the well-established effects is the effect of forced convection on dendritic growth. Just a moment, please. Now, on an example of convection, we can consider effect of reduced gravity and microgravity on the formation of microstructure. Forced is one of the key words in this convection. Forced means that we induce this convection in special environment and special equipment. And one of the well-developed equipments is electromagnetic levitator, which was installed in International Space Station in 2014. And we already have 6 years for the continuous experiments on this equipment and this facility. And we compare results obtained on the ground, in reduced gravity and in microgravity. So this is just a comparison now. We have no well-established outcomes, and this is one of conclusions I will make today or next week, because this lecture is rather big, and that in principle, we have no well-established conclusion at which conditions we have better microstructure, on the microgravity or on the ground. I will show you results of microstructural investigation, but today we start to learn effect of forced convection on the dendritic growth. So as before, our lectures are on this side. I already put this 5th lecture on this internet site without movies. We have 2 movies in this lecture, and I skipped these movies, just the pictures included, because with these movies we have 2070 megabytes.
We can't see picture.
Yeah, I put the picture.
Oh.
Так, Yundong joined to us. So, content of our lectures.
Oh.
Hi, Yundong.
Hello.
Hello. Thank you very much for your joining. Now, we have content which shows us motivation and types of convective streams to remind us which types of convection we have. I'll show you results from experiment on the ground and in reduced gravity and under microgravity. From this point, I have to stress on the fact that reduced gravity means several seconds we can make microgravity conditions in parabolic flights. But microgravity, this gravitation, this is a reduced gravitational force to the 0.01 G on the International Space Station. And I'll show you the direction of streams and how they influence on the microstructure formation in droplets processed in electromagnetic levitator. I'll show you a couple of models, which first of them can be solved numerically, and second one can be solved analytically. And I'll show you results of this modeling and analytical predictions. And then we can give the conclusion about these investigations. Once again, our lecture is a little bit big, and because of this, I think we can divide it in two parts. Let's see. So, motivation for the research on the reduced or microgravity conditions. So we have nickel aluminum alloy and samples processed in electromagnetic levitation facility. One of them is on the ground, and second is in microgravity. The initial starting and the cooling for nucleation is almost the same, 80 Kelvin and 79 Kelvin. But the structure is totally different from what we can see. So in 1G, first of all, we have deformed shape of the droplet due to the microgravity, due to the gravity. This droplet will be deformed in such a case that it represented Earth-shaped geoid. In this case, we have very weak electromagnetic force, which we need to have levitation. Because of this, we have an almost spherical shape of this droplet. In this case, we have a big shrinkage area, big shrinkage defect, porous, but the bottom part or middle and bottom part of this droplet is rather dense in comparison with the microgravity processed droplet. So we have distributed pores in this case and not dense microstructure in this case. And we try to measure the, for instance, micro hardness by Vickers method. And we saw that this part of sample exhibited much better micro hardness than in this case. Moreover, diffusion, percolation, or electric resistance, electric conductivity, also in this case is better on the ground than in this case. However, corrosion resistance is better in this case, in the case of droplet processed in under microgravity conditions. It means that it depends on the necessary, it depends on applied material properties we need to have in the materials. Microgravity conditions or ground conditions could be better. This is one of outcomes. So this is a scale, 1 millimeter in diameter, these droplets of about 6 or 7 millimeters. So in both cases, we measure it kinetics of solidification by the front propagation. In a few minutes, I will show you the method how we can measure that, but you can see on the ground we have points much higher in the region from 0 to 120 Kelvin, bigger than the points, higher than the points measured in reduced gravity conditions. So, and then a model without convection can predict well the data in the whole region of undercoolings, measured on the microgravity and on the ground, beginning from some undercooling. What does it mean? It means that we can say that these points were influenced by convection, and convection influenced in such a way that we have increasing the velocity of crystal growth in this case. And we can say that's beginning from some undercooling beyond the 120 in this case. These points and these points confluence at one curve. It means that the influence of convection doesn't work anymore beginning from beyond the 120 Kelvin. It means that convection may influence in some established region of undercooling, and probably, and we will show that by the direct calculations below, that convection may influence on the kinetics of crystal growth, crystal propagation, only in the region where velocity of stream, velocity of the flow is comparable by its magnitude with the crystal growth velocity. For instance, if the crystal growth velocity 20 centimeters per second, then stream should be of this order. For instance, 10 centimeters per second. In this case, we can expect dramatic influence of the flow on the crystal growth kinetics. This is a motivation in order to investigate more deeply microstructure and kinetics of melting and solidification. So, which types of convection we know? First of all, I would say that the convection is one of the complicated phenomena in macroscopic physics. It is always three-dimensional. If we have three-dimensional object, then it is the nature of convection is three-dimensional. Of course, we have several equipments with thin films where the convection can be developed as a two-dimensional structure phenomenon, but usually this is a typical three-dimensional phenomenon. So, and if we collect the types of convection, we can say that there is a natural thermal or chemical gravitational type of convection, forced due to the imposing of external fields, for instance, acoustic or electrostatic or electromagnetic fields. Marangoni convection due to the difference in surface tension and chemical composition. Also vibration convection in gravity fields. Taylor type of convection, stability and unstable cells of this convection are studied in many equipments in order to predict transition from laminar to turbulent flow. Also the same for Taylor-Couette flow. This is also well established object in order to learn transition from laminar to turbulent flow. Also, there are super macroscopic streams in oceans or in atmosphere, which can be learned experimentally or by methods of mathematical modeling, and of course mantle convection. If the ocean, if the streams in ocean or in atmosphere can be of the order of several meters per second, in the core of our magma, in the core of our Earth, we have very sluggish convection, which, however, drastically influence on the magnetic poles or other effects of the living conditions on our Earth. So in the mantle or in our magma in the Earth, we have several millimeters per year. Velocity is of the order of several millimeters per year. Sometimes we can predict that the magma moves with 1 centimeter per year. It is not so fast as in ocean or in atmosphere, but it drastically influences on our life on the Earth due to the well-known factors. So now we can say that even these types of convection could exist during the phase transformation due to the crystal growth or melting of crystals, and there are different regimes in pattern formations like solid chemically diffusion limited pattern formation growth, thermochemical transitive regime between chemical diffusion or thermally controlled growth, pure thermally controlled or mixture between thermally and kinetically controlled growth also exists. Purely kinetically limited crystal growth exists. And if we take into account that there is a growth of different crystalline symmetries and the crystallography can be crystallographic preferable direction of melting or growth can be changed with the change of driving forces of phase transitions, the task becomes very, very complicated. So types of convection and regime of growth are absolutely crossing in a very complicated manner. Because of this, we only consider so-called forced convection, which influence on the normally to the chemically diffusion limited growth. So with this aim, in approximately 40 or 45 years ago, in German Aerospace Research Center in Cologne, there was a group which developed electromagnetic levitation facility. Then this facility was distributed everywhere in Japan, in China, in the United States, but the first electromagnetic levitator were well developed in Germany. I have to say that from the historical point of view, in principle, I have a book which I showed my German colleagues, and then they were surprised that first electromagnetic levitators and droplets processed in alternating electromagnetic fields were made in Volga, on the river Volga in Soviet Union. But the name of this investigator was Vogel. Vogel is German name. You know that a lot of Germans during the Katerina the Grosse were coming to Russia, and normally they were living in several parts. One of the parts was on river Volga. around the Saratov city. And in Saratov there was one man which in 70 years ago developed such equipment, and from historical point of view, these Germans, Russian Germans, were first who built up this equipment. So this equipment is established in several cities, in Dresden, in Jena, and in Cologne, mainly in Cologne. They can be installed to the other facilities, For instance, in Jena, we have stationary electromagnetic levitator. In Cologne or in Dresden, colleagues have a non-stationary electromagnetic levitator, which can be established to the X-ray or synchrotron investigations of their droplets in order to see whether so in situ measurement of microstructure overheated or undercooling droplets in order to find cluster structure, or to answer the question whether the cluster structure can be transformed and structural transformation exists in overheated or in undercooled liquids. During our one of forthcoming lectures, which will be devoted to the investigation of glass forming alloys, I will show you how the microstructure can be changed. But now I just make a general remark that such investigations can be made in non-stationary electromagnetic levitators in Grenoble or in Hamburg, where a special scattering devices exist, or special devices in order neutron scattering or electron scattering, which can measure and give information about cluster, atomic structure, or transformations in the liquid state. So these two pictures show electromagnetic levitator in Otto Schott Institute of Materials Research at Friedrich Schiller University, Jena. This is a general view, and this is a camera which shows us wie heißt Spule auf English?
Coil.
Coil, right. So this is a coil, and this is a, you may see, this is a special table at which we put sample, and then switching generator, we have alternating electromagnetic field which provide special force, Lorentz force, directed in opposite direction to the gravity. Gravity is directed down, and alternating Lorentz electromagnetic force of Lorentz directed upwards, and then if the power of the generator is enough in order to compensate gravity, then we can skip this table, and the droplet will be in the levitated state. So there is a special high-speed camera and pyrometer. This is a pyrometer which measures very precisely the temperature of the droplet, and somewhere here there is a high-speed camera which measures with a very high speed propagation of recalescence front. Recalescence front is a front of latent heat releasing at the tips of crystals propagation. So, and then we can see everything and recording on in the computer, and then analyze this picture from the high-speed camera. High-speed camera normally, it depends on the alloys. For instance, in the glass-forming alloys, the kinetics of propagative recalescence front is much lower. Kinetics is much sluggish than in normal, for instance, substantive alloys. Therefore, we adjust the camera to the concrete alloy, but normally speed of recording ranges from the several units or tens, tens, 100 frame per second up to the several tens of thousand frames per second. Then from 100 frames per second up to the 10 to 3 or 10 to 4 frames per second. It depends on alloy, as I told you. This is a typical equipment on the ground, and this is once again this is stationary equipment in University of Jena. However, this equipment was installed in Tempus facility in the special air buses belonging to the ESA, European Space Agency, and we test our samples in electromagnetic levitators during several seconds when this air bus goes up and then falls down. So now the air bus goes up in order to fall down. We have a Biscay Gulf close to France. It falls down. So there was just 20 seconds, and during these 20 seconds, you have to initiate triggering solidification of your droplets or measure surface tension or viscosity, electroresistivity just during 20 seconds. In principle, it's enough to have information because, for instance, with regard to solidification kinetics, such small droplets, several millimeters in diameter, solidifying 10 to minus 4, 10 to minus 3 seconds. Because of this, if you have your droplets in overheated state and it is already melted, and if you have some cycles in order to destroy inoculators in the liquid, or big clusters in order to destroy and to have a more or less homogeneous microstructure of liquid. Then you can cool down during these 20 seconds by injective cooling gas, which consists of hydrogen or mixture of hydrogen and helium. And then you can cool down and then initiate crystallization of your droplet during these 20 seconds. It's enough. The same for the measurements of surface tension. If you have already melted droplet, then air boost goes up and falls down during 20 seconds. You have microgravity conditions, but due to oscillating regime of droplet, we have alternating field, and it makes the droplet oscillating. And then due to this statistic for oscillation during 20 seconds is enough in order to make measurements and then recalculate surface tension of this liquid droplet. The same for electric resistivity or electric conductivity. So now a few words about measurements of the solidification kinetics. So once again, we have a coil, we have a liquid droplet. It looks like very bright because the temperature is very high. For normally we have about of 1000 Kelvin or 1200 Kelvin or even higher, depends on the metal or alloy. And then if we have spontaneous or triggering process of solidification, then we have once again propagation of recalescence front. This part is already solidified, so the solidification was by triggering from the south pole, and then we have propagation of the recalescence front. It shows like two-dimensional front on the sphere. In reality, this three-dimensional surface which propagates into the undercooled droplet. And then we see that the front propagates up to the south pole, up to the finishing of primary solidification. How many liquid remain into the intercrystalline spaces? It depends on the initial undercooling. I show you in the next transparency. Here I show you just a principal estimation of the solidification velocity, of the crystal growth velocity. So we have a nucleation center right here. It could be south pole, or it could be from the from the other side, from the west side, for instance. And we have trigger needle made from the same material as a droplet, and we can initiate crystallization from here, and dendrites or crystals propagate in the different directions and gives us recalescence front. This part is solid or two-phase state, because dendrites represent a very developed, very branched structure. In between we have remained residual liquid which did not solidify during the primary solidification. But for us it is very important to know the speed of the tips of the dendrites. And for instance, analytical theories predicts two main parameters of the dendritic pattern: velocity and dendritic radius of dendritic tips as the main parameters of primary solidification. And then we can correct the model in order to predict phase transformation in a good manner for practical reasons. By first experimental measurements, we can correct our theoretical modeling by these two parameters: velocity of dendritic tips, velocity of recalescence from propagation, and dendritic tip radius. So, and very simple, we have a diameter of droplet, for instance, 6 or 7 millimeters in diameter. And then we have a time which we have from the triggering starting time up to the time to the reconnaissance from coming to the North Pole or East Pole in this case. So as soon as we have time, and we have time due to the measurements by high-speed camera, then we can simply divide diameter of the droplet over the delta t, Tn minus T0, and then we can say something about velocity as a function of initial temperature, initial starting temperature when we trigger it of our process, or undercooling, because we know we always know the melting temperature of metal or liquidus temperature for the alloy, and if we subtract liquidus temperature, melting temperature, if we subtract initial temperature from the liquidus temperature or melting temperature, we can get undercooling, and then we can put 1 point for the one experiment velocity as a function of initial undercooling. Of course, we assume that we have rapidly coming to the steady state, because we always dividing by diameter over delta t, we assume that the whole process was in steady state, in stationary propagating velocity. Velocity comes very rapidly to its steady state value. Computation shows that this is true. If the total solidification velocity of the droplet is of the order of 10 to minus 4, 10 to minus 3 seconds, milliseconds, or 1/10 of millisecond, then the time for the coming to the steady state, to the constant velocity of the reconnaissance front is of the order of 10 to minus 6, 10 to minus 7 seconds. It means that we have only 1/100th or 1/1000th part from the whole time of solidification of this droplet. Because of this, this approximation works properly in undercooled droplets. So, what structure of the convective streams or rolls we have in the droplets processed by electromagnetic levitator? First of all, please take your attention for the shape of the droplet. So this droplet definitely was, this scheme is related to the solidification of the droplet under the gravity. Because of this, we have this nose and this geoid shape here. So this part comes down due to the gravity. So, and if we start our solidification from the bottom, from the South Pole, here we show the shape of the front of recalcitrance in pure nickel at the initial undercooling 89 Kelvin. So this is once again, this is a two-dimensional projection of the three-dimensional shape which developed inside the droplet. So anyway, we have dendrite, which grows in different direction from the triggered point. But before the solidification, we have specific structure of liquid flow into the droplet processed in electromagnetic levitator. So we have two tores. One of them is lies down. We have here equator, and we have second torr at the top part of this droplet. And very remarkably, in electromagnetic levitation facility, so once again, gravity directed downward is vector of gravity. So in this case, electromagnetic field acts in such a manner that we have two torrs at the bottom and top parts, and the velocity direction of streams normally directed to the down in the direction of gravity, but the crystals grows in this direction, opposite direction to the flow in this torr. And then we can see how the torrs deforms during the propagating tips of dendrites. And we can see in principle, we have almost always flow directed to the opposite direction to the growth. Streams show directed down around the dendritic tips, and dendritic tip grows up in the droplet. So in principle, this scheme works properly in many cases of triggering solidification. Here I show you the movie, which gives us impression about propagating fronts. This is a movie obtained by my master student, Philip Paul, in 2017. He was working here under the master thesis during 1 year in our institute, and I was supervisor of him, and he made a lot of measurements of aluminium nickel alloy solidification and iron silicon. So we can see, I will show you now. We've seen the liquid structure, and we can see that here we have slag. Here we have oxides of aluminium oxides on the surface, and they exhibit complicated structure of liquid streams at the surface of this droplet. By the way, one of the methods of measurements of the liquid velocity is to put special particles or oxides on the surface of the droplet, and then we can recalculate velocity at the surface to the bulk stream velocity. But anyway, it was naturally. We did not make something special. We only have seen this movie, and I selected this. We have several hundreds of movies, and I selected this movie in order to show that these oxides shows us complicated curls on the surface of this droplet. You can see, and then at some point we got bright propagation of this front, because in this part we have releasing of latent heat, and latent heat makes this part more brighter than the dark part related to the remained undercooled liquid. Stop. So that's it. We have measured. We have made measurements of this interface velocity as a velocity of dendritic tips once again. And then we can say that the primary solidification begins and stops during some time for given undercooling. So this is a typical measurement, typical propagating front of recalescence in our case. So the Hult's cycle for temperature time we show here. So we have room temperature at which our droplet exists. As I told you, we put it into the special holder at the special table, and then we switch in generator, and due to the induced current, electric current, once again we have a solid droplet at the room temperature. Then due to the induced electric current after switching the generator in EML camera, this droplet will heat up from room temperature up to the first critical temperature consistent with the solidus in the case of alloy. In the case of metal, we have just one critical temperature, melting temperature, but anyway, in this case, slope of heating is decreases due to the fact that it is not go like that one. It is go with smaller slope due to the fact that we need to bring a lot of heat in order to melting, in order to destroy atomic bonds in the crystal lattice. Because of this, the slope will be smaller. However, if we come to the complete melting at the liquidus temperature, when we have liquid droplet, in this case we have two-phase droplet. In this case, over the TL liquidus temperature, we have homogeneous, macroscopically homogeneous liquid, and if we overheating our droplet at several tens or 100K normally, then we can theoretically destroy big clusters existing after melting in the liquid. This procedure can be repeated several times, and normally we have several cycles over liquidus temperature, which can theoretically, in principle, practically destroy all or deactivate all inclusions or destroy big clusters in the liquid in order to avoid maximally avoid heterogeneous nucleation in the liquid. We would like to undercool at several tens or hundreds Kelvin. Because of this, we have to avoid heterogeneous nucleation due to the containerless nature of this process in EML, and by destroying the cluster structure of the liquid. Then we can inject the cooling gas in our camera, and this droplet will be cooled down up to the liquidus temperature. We are going below at several tens or 100 Kelvin, because we can undercool very deeply due to the, once again, containerless processing and destroying big clusters in our droplet. And at some temperature, Tn, nucleation temperature. Nucleation means we start nucleation by triggering of our droplet from here, from this south pole, and then during the very short period, this is a not exact vertical line. This is a line with some slope, but the slope is not well visible the period of recalescence from nucleus temperature up to the temperature to the plateau here is very short. So, for instance, this period is several minutes or half of the hour, takes several tens of minutes or minutes, and this period, I told you, primary solidification is duration of this primary solidification is about 10 to minus 4, 10 to minus 3 seconds. Because of this, the slope is not visible here. But there is a period of from recalescence to coming to this point, slightly below liquidus. In the scheme, we showed that this is a liquidus temperature. Then, due to the further cooling, we have decreasing temperature to solidus temperature. In this case, we have finishing of primary solidification of dendrite with, you see, residual liquid here. And then we can cool down rapidly to the room temperature our solid droplet. And the residual liquid will be solidified with a different content in comparison with the main stem and branches of dendrite. Which types of plateau duration? This is a delta T plateau PL. Delta T PL, this is a time duration at the plateau. Which types of plateau we have? So classical type, when we cool down up to some nucleation temperature, which is with the undercooling smaller than the hypercooling limit. Then we can start recalescence and comes to this crystal temperature, which is around slightly below liquidus temperature. Then we can stay at this plateau and cool down again. Let me remind that hypercooling temperature is or hypercooling limit or hypercooling undercooling is defined by the ratio between latent heat released during the phase transformation or during solidification and over the heat capacity. And if so this is a specific parameter. Hypercooling is a specific parameter of every material, every metal, or every semiconductor, or every alloying system. Latent heat divided by heat capacity. Not for normal alloys, it takes 2 of up to 400 Kelvin. 200 up to 420, 450, usually this value of hypercooling. So, and if the initial starting undercooling from TL defined by TL minus TN, initial undercooling is smaller than the hypercooling limit, then we have this scheme. We heat up to the temperature around liquidus temperature and then stay at the plateau several milliseconds or seconds or even 1 minute at the plateau and then cool down. It depends on the cooling rate of our cooling gas. And once again, hypercooling is a parameter which gives us ability to estimate the adiabatic temperature of solidification. So hypercooling is equal to the adiabatic temperature of solidification. What does it mean, adiabatic temperature? It means that with the reaching adiabatic temperature, so Tn will be consistent with the adiabatic temperature. We don't need to have outer removal heat released during solidification. Undercooling is so high that it accumulates all heat released during solidification. Because of this, we don't need to have boundary or outer removal of the heat from the sample. So there is another type of crystallization which is consistent with hypercooling. If the initial undercooling defined by the difference between liquidus or melting temperature and nucleation temperature is equal to the hypercooling, then we have no plateau duration at the crystal temperature. We have only one point, so recalcitrance lead us to the point, and then we undercooling is enough in order to accumulate all latent heat, and we don't need to have outer removal of the heat released during solidification. Because of this, we have only one point and then further cooling down. The same situation we have if the temperature is, nucleation temperature is below adiabatic temperature, and the cooling is below the hypercooling, then we are not coming to the normal standard crystal temperature around the liquidus temperature. We are below, but with this point, and we go down. In several cases, we have amorphization in this case. So undercooling is so high, then we come to the freezing liquid in this point and go down. So glass temperature is below adiabatic, usually adiabatic temperature of solidification. These types of microstructure exhibit as this type of temperature time profiles leads to the different types of microstructure. And I will consider only one type of this type of microstructure when the undercooling is smaller than hypercooling limit, smaller than adiabatic temperature of solidification, and we heating up to this temperature and should wait in order to remove latent heat and by outer surface of the droplet due to the cooling gas, and we should wait here. And then primary solidification leads us to the main part of the droplet, as a solidified part consisting of dendrites and residual liquid here. And then if we say that there is a instability of dendritic pattern, it occurs always. In principle, every construction, every body has vibrations, self vibrations. And if these self vibrations can lead to the instability, then this pattern can be destroyed, right? So, and then we can calculate time for unstable structure, building unstable. So, and if the time for instability smaller than the time of staying at the plateau, then instability comes and we have refined structure. So this primary structure destroys by several parts, several units of this structure. And then we can see gray as after complete solidification, we have refined microstructure. However, if the time for instability of structure is bigger than this plateau duration, then our dendrites could be stable, and this structure shows us coarse grain with big graining after primary solidification. So, and we have two different structures. There are special theoretical estimations of this process, and there are specific regions of undercoolings at which we can observe very specific analysis should be done for that. So, which type of microstructure we can get? As I told you, normally in electromagnetic levitation facility, our stream lines of the flow directed to the opposite direction to the crystal growth. And we can see difference in microstructure solidified in stagnant melt. This is a two-dimensional modeling using by two-dimensional phase field modeling, and microstructure solidified under the flow imposed at the top boundary of computational domain. So in the case of solidification in stagnant melt, we have symmetric pattern developing in the direction of preferable crystallographic directions of growth, and then we can get this symmetric pattern. However, if we impose the stream at the top boundary of the computation domain, we have a flow here, and we can see that the upward branch develops faster than other ones. Upward branch develops faster than other ones in all cases of modeling, on all cases of anisotropies. Let me say that these pictures shows us different strengths of anisotropy of crystals. So this strength is much higher than this one. This is intermediate strength of anisotropy. But anyway, in this case, and then we in this case we impose flow, and we can see that upward branch develops much higher than other ones. In three-dimensional modeling, we can see the same phenomenon. In the stagnant liquid, we can model the crystal which absolutely symmetric in all 6 directions. These branches developing in the preferable crystal growth direction, which are 100 in the case of pure nickel. That was nickel dendrite modeling by phase field modeling. However, if we impose the flow at the top surface of the three-dimensional computational domain, we can see that this branch develops much faster than other ones, like in two-dimensional case. What is the reason for that? So there are several answers which are absolutely demonstrate absolutely the same tendency, absolutely the same mechanism of the developing branches in the case of flow. In the case of flow, first answer, in the case of flow, we have fast removal of the latent heat released at the interface, right? And if the heat is releasing in the region of flow which is with the streamlines downwards, then this heat distributes much faster for this branch. This is a natural. However, if we see in this case, downward branch is developing much slowly than these ones and even these branches, side branches. Why? Because we have stagnant zone here. So heat removal in this direction, heat removal in this direction, and in this region shows us deeply stagnant region at which growth of branch suppressed due to the releasing latent heat. Latent heat released and increases temperature. Temperature increases and the cooling decreases, and this part down part of dendrite grows. And the second answer to why we have developed branch looks into the consideration of isotherms around the dendrite. So why? Because isotherms shows us direction of thermal gradient, right? So the much higher or warmer isotherm lies around the dendrite, and the much cooler isotherm lies behind the interface, and the gradient is directed to this direction, from the cold to the warm part of this heat field, and by this direction crystal branches grows. So velocity is proportional to the temperature gradient, right? We know that from the boundary condition of the Stefan problem. Velocity is proportional to the thermal gradient. So in the case of stagnant liquid, heat propagates into the well-established directions dictated by preferable crystallographic directions, and we have symmetrical heat field around the dendrite. However, in this case, in the case of imposed forced flow, this part of isotherms are deformed, and then these will be much denser, and in much denser isotherm field, we have higher gradients around the tip. Because of this, these higher gradients around the tip growing into the opposite direction to the flow, we have deformed isothermal field, and then by these deformed higher gradients, dendrite tip grows faster than other ones. By the way, if we compare the velocity of these side branches, they are almost the same like in branches growing in stagnant liquid. However, this branch grows much sluggish, with much smaller velocity than these ones, and of course these ones. So this is a typical influence of the flow imposed on the growing crystal. And normally in microgravity, we reduce drastically flow induced by electromagnetic forces. And we have normally a structure developing like this one. On the ground, we need to compensate gravity force by high electromagnetic power induced by our coil, induced by our generator. Because of this, the liquid flow after melting is in the intensive motion, which of the order of several millimeters, centimeters, or 10 centimeters per second in the droplet. And even for 10 centimeters or even units of centimeters per second, we have a turbulent flow into the droplet. Below there, several tenths or several units of centimeters per second, we have intermediate laminar turbulent or laminar flow in our droplets. Because of this, which type of model we can use, it depends on the flow intensity. And for today, I would say we can finish by this transparency. I just explained you the scheme and the main governing equations in full statement of which we can solve them by numerical method. So these are typical convective schemes for flow imposed into the opposite direction to the growth. U is flow average mean value of the flow velocity, which is directed to the growth direction. V is the velocity of the dendritic tip, and rho is diameter of the dendritic tip. And I told you, in principle, we can predict numerically and analytically these two main parameters which are measured experimentally. These measurements this parameter V, velocity, is measured due to the measurements of high-speed camera, and if that pattern was not transformed, we can expect that primary dendritic radii remain the same, and we can measure them statistically, and we can say what is diameter or radius has a primary structure as a function of undercooling. So this is a scheme. However, this scheme is true for laminar forced flow. In turbulent flow, we have curls, and we have a tip imposed by average value of U star around the dendritic tip, and we need to use other boundary conditions at the dendritic surface that here are shown. Here are shown transport of mass. There's a hyperbolic equation for the concentration and parabolic equation for the heat, which takes diffusive part of transport, right hand side of these equations in the liquid. This is the diffusion part of transport of mass, transport of heat, and convective parts. So V is the vector of velocity W. W is the vector of velocity. One of components has V in the direction of z-axis. And we have, in a very simple case, Navier-Stokes equation in the special approximation, which shows that velocity changes in vector of the velocity changes due to the imposed flow in this direction as a function of pressure and a function of viscous term. By the way, here I have a mistake, because here should be not gradient but Laplacian. I have to correct this equation. Here should be Laplacian, of course, like this one operator on the velocity. So, and we have here, and this is a vector, these scalar equations and this vector equation. These equations related to the liquid part of solidifying droplet. This part is related to the solid part. In the solid, diffusion is much more sluggish. Because of this, we can neglect it. Several orders of magnitude sluggish, like in liquid. But heat should be heat propagation into the solid phase should be taken into account without this convective term. In addition to this Navier-Stokes equation, we have to use continuity equation, which shows that divergence of the velocity vector is zero under the constant and the condition of constant density of the liquid. If we integrate this system of equation, we can get condition at the interface, and you can see these are, in the case of laminar flow, exhibit just conductive conditions at the interface. There are no V or W at the surface. They are zero because it is not so high velocity like in this case. In this case, boundary conditions should be rather different. They should include U star in these boundary conditions, because at the surface U is not zero due to the high intensity of the flow. So this is a condition between temperature, concentration, curvature of this interface, and kinetic torque. Anisotropy can be taken as an anisotropy for the cubic symmetry, and conditions, far field conditions, which shows that the liquidus concentration is far from the interface, is nominal zero concentration, and the temperature far from the liquidus temperature at the interface, liquid temperature at the interface, is also constant. So then vector of the three-dimensional W velocity is released as a middle or mean value of the velocity. Now I have to say that our time was finished for this lecture. Please ask me your question if you have.